Okay, well, I'd like to thank everybody for joining us for our CLIVAR Climate Risk Working Group, the second one of our webinars. My name is Andy Dessler, and on behalf of the other organizers, Adam Sobel, Amy Clement, and Alex Hall, thanks for attending. We've got some really two good talks today. And the last webinar, we had 3 talks, and we didn't have as much discussion as we'd like. So this time we scheduled 2 talks. So the hope is there'll be lots of time for discussion. If you have questions, you can type them into the chat at any time, or after the talk, you can raise your hand and we can, we can call on people and we can have a discussion that way. Also, make sure everyone's mic is muted. We've been doing this for years. People know to do that now. And with that, let's go ahead and get rolling. Our first speaker is my friend Dan Kirk-Davidoff. He works at the Electric Power Research Institute. He's a senior technical leader there, and he studies how climate change impacts the electric power system and renewable energy generation. Before joining EPRI, he was at the University of Maryland, and he also had a job developing forecast systems for wind and solar generation in private industry. He holds degrees from Yale and MIT. And with that, I will turn it over to you, Dan.
Thanks so much, Andy. Much appreciated. So I have a bunch of slides in here. I'll try to, but I want to be timely. So let me just start by explaining Climate Ready is an acronym, Climate Resilience and Adaptation Initiative. It was started just about the time that I arrived at EPRI, so 3.5 years ago, back in May. And it, as you'll see, it involved both EPRI's members. EPRI is a membership organization of utilities and grid operators. And also we had a big advisory group of experts in the field to help us out with this. And let's see if I can advance my slide. Here we go. Yeah. So I tend to think of Ready as being organized in a way somewhat analogous to the IPCC. Whoops. So we have physical data, physical climate data and guidance in workstream 1. We have power system asset vulnerability assessment in workstream 2. So, workstream 1 is what is changing and how do you know about it? Workstream 2 is what are the impacts of those changes on the power system? And then workstream 3 is what do you do about it? System modeling and investment prioritization. While EPRI tries to make as much of our material as possible freely available to the public, because we're a membership organization, we have a bit of a free rider problem when we have to make sure that members get some stuff. We can't make everything public, but for Climate Ready, we were able to make everything public. So everything you see here, there are some real links in this document. I provided the PDF version of it to Alyssa, and you'll be able to, find all of this stuff on our website. I'm very, very deeply interested in and all of us are. This was a big, big project of which I was a small player. Maintaining this project in an up-to-date way. We're very interested in getting your feedback on anything that looks like it could be improved or updated. But we've had our, sort of final rollout of the Climate Ready process this summer in August. And the idea is that most of the material in this project will transition to one of EPRI's regular programs. We have, consecutively numbered programs that have been developing over the years. I think Climate One is, Program 1 is like, transmission, and that's existed for a really long time. And this will be Program 2 on, climate impacts on the energy system. So we had about 40 members of 40 of our members who actively signed up and supported this project. We had a very large number of events, between online events, but also lots of in-person and regional working group meetings. We had 112 people who were our Climate Ready Advisory Group participants. Andy was one of them, much appreciated. We had a lot of deliverables, many of which you'll see in the next few pages, and we got a reasonable amount of press for it. So the members who supported this program were distributed all over the US, and also we had a member in the UK and in France involved, and Canada, several in Canada. These are all their logos over here. And then this was the affinity group, all the people we turned to outside of EPRI to give feedback and input to the recommendations that we made under this process. So you can see this is quite a large group and included a whole bunch of university groups. Okay, trying to move my mouse on the screen, but it's not cooperating, but that's okay. Lots of universities you can see on the lower right-hand corner, the National Center for Atmospheric Research, the National Renewable Energy Lab, all sorts of groups were involved. And those groups included not only academic and research organizations, but consultants, industry groups, environmental NGOs, and a bunch of other experts in the field in various ways. So this kind of final rollout product, the climate ready power framework, we think of as having three modes of helping, so guidance, references, and tools, and then for each of the work streams we have guidance, references, and tools, and I'll show some charts along those lines. So for example, this is here's a kind of overall diagram of all the things that are form a part of the climate ready power framework. So work stream, this is the overall ready process. This is work stream 1, climate data in this column. In the third column we have asset vulnerability, that's work stream 2, and in the fourth column we have what do you do about it, system risk, how do you calculate that, and how do you make investment decisions on the base in order to mitigate system risk. And then the products that we have are divided into guidance, references, and tools. Some of the tools are, we have some code bases. For instance, the climate risk screening tool, there's a GitHub site associated with that. There's some Python code that people are free to, download and make use of. And then some of the other tools are, a little bit more sort of data and focused. So climate-related vulnerabilities and adaptations for electric power system assets tool. If you click on that, you'll see there's all sorts of vulnerability curves for lots of different kinds of infrastructure where you show, our understanding of the best engineering standards that would relate a climate change to the impact on a system component. Over here, this is Climate Data User Guide was the one I'm most familiar with. So that was a guidance document. It's essentially a kind of encyclopedia of climate changes that are of relevance to the energy system. So it includes chapters on, how a climate model works, but where can you get a hold of relevant climate information that we expect to be applicable to, near future conditions, the conditions of the next few decades. It includes a glossary, it includes sections on climate statistics, et cetera, and so on. And then let's see what's another, so please, take a look at these things. If you go to epri.com/READI or follow the links in the document that that I hope will share as a PDF, you can get to all of these places. There's also kind of an all-in-one entry. If you look up Climate Ready Compass, you can get there. It has a phone compatible site. We're really trying to make this useful to people. So I don't mean to be sheepish about that. That is really important. We want this to be used. We want it to be useful. And so that means that people need to be able to get a hold of this information in ways that are convenient and actionable and quick. Where I'm just going to walk through a little bit more on the individual work streams. I'm looking at my time. Looks like I have about 10, 12 more minutes. Let me know if I should cut it shorter than that. So this is work stream 1. We're looking at climate data. How is climate changing? What do we know about how climate has changed in the past? How does climate change in the future? If you want to make an assessment of how climate change will impact, some particular bit of infrastructure, how would you go about that? So we have the Climate Data User Guide, which I just described. We have this climate hazard and exposure assessment guidance, which is a little bit more focused on, high impact, the kinds of high impact events that are of greatest consequence for energy systems. We have a climate data gap assessment that looks at kind of the level of confidence that you ought to ascribe to different kinds of climate change impacts as we understand them in the future. So with a little handy graphical guide to, better understood in green, less well understood in yellow, and we really could understand this a lot better in red. So, for example, wind gust is something that's just really hard to get out of a climate model. They're not going to explicitly model it, and doing it in some statistical way on the basis of an output from a climate model is also quite tough. On the other hand, if you want to understand how the temperature of cooling water is going to change over the future, that's a little better understood, and things like expected summertime temperature change in some part of the world, that's even better understood. We have a climate data inventory that goes through like all the different places where you could reasonably expect to find high quality climate data, and has kind of paragraph level descriptions of those and links. And we have a wildfire inventory tool that has a lot of material about our understanding of wildfire in its relationship to climate change, and in its aspect as a hazard to power systems, and in its aspect as a hazard that can be set off by power systems if adequate care isn't taken. Right. This is a similar graph, a chart for workstream 2, the impacts assessment. So we have a bunch of different forms of guidance. Some of these documents are, specific to a particular kind of power system infrastructure. So our climate vulnerability assessment guidance for nuclear power plants is, heavily focused on temperature. There's a lot of material in there about temperature of intake water, which has been a big concern in all over Europe a couple of summers ago when it was super hot. And is of great interest to operators in the US as well. We have more general references like these fragility curves for physical climate risk in the power sector, and assessment vulnerability literature review series that really goes into depth into the basis for these kinds of power curves that we present up here. And then there's a tool that gathers together a lot of this stuff in a convenient website and has links to all of the other material. So I'll just go through a little more detail in that section, because I thought this is the kind of material that might be a little bit less familiar to folks in our working group. So we're trying to understand what power system assets might be vulnerable to which kinds of weather. So that's a big, right, a big chart where you have asset, hazard, and you really try and understand which of these things is of most concern and is most actionable for folks who have responsibility for those assets. So what's the specific relationship between a weather hazard and an unwanted outcome for each specific asset, and what factors can modulate or those relationships, and what adaptation strategies are available to minimize unwanted outcomes and costs and benefits associated with different adaptation strategies. Online demonstration tool for this kind of stuff listed here. On a kind of a different note, but more up my alley, I did a bunch of work understanding the relationship of wind and solar variability on climate variability timescales. So making maps over the U.S. of the relationship between high and low wind months, high and low solar insolation months, high and low energy demand months, and how those relationships and correlations vary in a map across the United States. There's a nice story map presentation of that stuff that's linked here. Really interesting thing to look at. These patterns aren't the same everywhere. In some parts of the country, hot summers are associated with windy conditions, and in other parts of the country, hot summers are associated with less windy conditions, and likewise for winter. And you need to do those assessments in advance if you want to understand the behavior of the system at large in its aggregate to climate variability, whether related to climate change or not. We also spent a bunch of time characterizing impacts of high air temperature on inverters and batteries and other things that are air cooled, right? So you need to understand fragility curves, not only how well does the system respond, but what are the probabilities of system failure, and how are they influenced by temperature and other climatic conditions. Now, finally, workstream 3 develops a framework to prioritize climate resilience investments by integrating all of the information on vulnerabilities and kind of frequency of hazards and that sort of thing. So we have planning guide for power systems. We have an investment guide for power systems. And again, the question for all these things is, there's a general understanding that it is certainly the case that a lot of climate change impacts, but even just the impact of climate variability in our system could be greatly reduced with thoughtful investment that is aware of the probabilities of certain kinds of hazardous events. And I think everyone understands that we could reduce the impact of climate change, and we could also reduce the cost of climate extremes, whether modulated by climate change or not, on our energy system by more thoughtful design of our system and its vulnerabilities to climate extremes. But in order to fulfill that, you really have to go down every rabbit hole and understand, how much should we spend making a system where trees don't fall on power lines versus how much should we spend on building a system where ice storms don't interrupt the supply of wind power. These are all decisions where you have to weigh the cost and duration of what you're able to do to make a system safer against how much safer will that actually make the system? How much more reliable will that actually make the system? And we've tried to get into lots of details and go down lots of rabbit holes in these documents, but that task will never end. There's an awful lot to be done, and of course the science and the engineering changes depending on both our understanding of climate hazards and their frequency and our understanding of our evolving technological mix and our assets. And that is my last slide. So I did kind of race through that, I realize now, but that leaves time for questions and clarifications. So if anyone has any of either request, I'd be happy to address them.
Thanks so much, Dan. This is Amy. I'm going to handle the questions. So please, you could either put them in the chat or you can raise your hand. So Adam can kick it off, and then don't be shy. Put your questions in the chat or go ahead and raise a hand.
Thanks. Great talk, Dan. So much stuff there. One thing I couldn't quite tell, I saw that you had original stuff for like the vulnerability curves and stuff. Is there original climate data in there? Did you guys do downscaling or anything like that? Or is it based on links to external things and sort of explanations of how to use them?
Yeah, I mean, for several projects that I've been working on recently, we've been experimenting with downscaling techniques, not in a terribly original way. There's some off-the-shelf AI-based techniques that we're looking at, and I've been playing with for wind gust, for example, and it's really challenging. Like so far, I haven't found something that helps a whole lot relative to ERA 5, for example, when comparing to observed wind gust. But for the most part, the climate data guidance that we've given is to existing projects, and it's been quite a stretch just to keep up with what's going on in the field. However, whether you call this downscaling or not, we have spent a fair amount of time coming up with our preferred in-house bias correction procedure to go from climate model. It is kind of a downscaling procedure because it's going from climate model data that may be only available in daily form, so like high and low temperature, daily high and low temperature. The power system often is going to want to have that in hourly format, especially for models of system behavior. Those are typically done with like either in the old days it would be a TMY. These days we're moving towards doing 10 years of 8760s. You pick a bunch of years that you think would be reasonably challenging, that kind of thing. So if we want to adjust those to the future, we have to have a way of taking forward-looking climate model projections and bringing those to an hourly level. And so we have a quantile delta mapping method that our team has put a lot of work just into understanding and working with, and seeing what comes out of it. And we discussed that in the climate data user guide and a couple of other places. We have a recent publication about it, and that's what we use. So it's not that it's rocket science. It's just the distillation of what we've been able to look at out there, what currently exists if you want to get an hourly time series out of a GCM result. but it's our sort of house method for doing that.
Thanks. So like just quickly follow up. So grossly speaking, if I'm a utility and I want to make use of this, it sort of tells me how to go to external climate data sources. And you have then information on how various power components respond. I mean, you made some original vulnerability curves and stuff, and it's sort of guidance on. I have to have some in-house capacity, but this will help me figure out how to do that. Is that sort of how you characterize the user relationship?
Yeah, that's right. I mean, we have an in-house climate analysis toolkit that we've put together of Python tools where we're just trying to have this able to be pretty turnkey for our usage, and that's should be really clearly documented. I think our desire would be to make that as publicly available, and I kind of think the code probably had to be done for the publication we did. I would need to double check that. But in terms, there also are actually at this point a lot of. I just saw a question in the chat from Paul. Are you working with recently available high resolution dynamically downscaled projects? Yeah, we've looked a little bit at CONUS 404 for our own internal validation purposes. We'd love to see and WSD3. We're aware of that. There are also a bunch of other high resolution downscaled data projects. There's the NASA one, which I'm just having a brain fart and forgetting the acronym, but there are a couple of ones that we make pretty regular use of that are out there. Some of them are more comprehensive in terms of like sampling CMIP6 than others. So that's one way in thinking about these things. And of course, like CONUS 404 is just a single iteration. A single downscaling of Verify, but I think that's terrific, and it's one of the things. Adam and I have had this conversation in the past. I think one of the things that's most exciting about the capacity to develop global models at something like kilometer resolution is the potential to do reanalyses that cover the historical period at that kind of resolution, and will have maybe better fidelity in terms of intense weather events. I'm not thinking of DCP-30. I'm thinking of what is it called? It's like not NASA NIST, NASA Next, right? That's a bit of an older project. It's not a super high resolution, but I think, as I recall, it had it's sort of close to Aerofire resolution. That one, right? Yes, Paul. NASA Next GBDP. Yeah, I think so.
Thanks.
Okay.
I just wanted to, I think Radley had his hand up since earlier. Are you there, Radley?
Yes, thank you, Amy.
Okay.
Great talk, and I guess somewhat sort of following up from Adam's question, your response. I definitely think of this, as we all would, as a sector where a lot of the users, expect, need, quantitative information, certainly. So I'm just sort of curious how you balance, maybe especially for some of the more challenging variables like hourly wind, or instances where you need a multivariate frame. How do you handle issues where you really feel like no downscaled product, even if it samples, all available GCMs, is likely to really sort of give anything like the true range of full range of possible outcomes? How do you handle that? Is that in the user guides? Are there instances where you say, well, here's where you can go for quantitative, but don't think of it as a true probability? Are there instances where you kind of discourage try and use model outputs and steer people towards scenario approaches if they can? Just sort of curious generally about those categories of questions.
I mean, as I'm trying to think, it's been a while since I was heavily involved in writing the user guide, but it's been a while since I read it over, so I have to remember what's in it. We've certainly been thinking and talking about the difficulty of assigning particular probabilities. We want, it's a big open question, like what is the right way to do a return period for an extreme event in a climate that's, that you think is changing. I don't think, we have like a closed answer to that question. I'm trying to think where I'm going to take that home and think about it and try and get back to you with. We definitely provide sort of recipes for, kinds of weather, like here are some places where you can look and here are the concerns. And some of the concerns would be things, we don't know what we don't know type concerns that you're getting at. But I think it would be good to have a sort of a general answer to that. And I think, it is like I showed you that example of like high confidence, medium confidence, low confidence. So we have things like that which would certainly apply to the questions that you ask and are, and address the specifics of, the confidence we would have in specific kinds of weather hazards. But I'm not sure it's quite really quantitatively addresses the question you've asked. So I want to take that home and think about that some more. Thank you. And there was a question in the chat about, is there a way to get feedback? And yes, all these documents have a, do you have a question button? Certainly the user guides, and we're very interested in getting feedback and moderating, changing material in response to it or adding material.
Okay, in the interest of time, let's move over to Bob's talk.
So let me introduce our next speaker, my friend Bob Kopp. Bob is a distinguished professor at Rutgers, specializing in sea level change and climate science. He directs the Megalopolitan Coastal Transformation Hub and is a founding investigator of the Climate Impact Lab, which assesses climate change economic costs. He was a lead author of the 2021 IPCC 6 Assessment Report. He's a fellow of the AGU and the AAAS. And really looking forward to your talk, Bob.
Great. Thanks, Andy. So I decided I would give a talk that's actually similar to one I gave. Some of you probably heard at JPL last year, but Andy couldn't remember what I had talked about there, and I think it's still useful. So we're going to talk about usable sea level rise projections. One of the challenges with sea level rise projections, as opposed to some of the other sources of climate information that can be taken straight out of Earth system models, like we just talked about, is that there is no single highly resolved process level model that models all of the major effects driving sea level change. You have to take into account not just atmosphere-ocean dynamics, which GCMs do pretty well, but also changes in ice sheets, which they basically haven't done, and coupling ice sheets and GCM still represents a scientific frontier. Changes in land water storage and vertical land motion, which simply isn't a process that GCMs do. And so one of the things we've been doing for about 12 or 13 years is working on frameworks to integrate multiple lines of information to produce sea level rise projections that account for all of the major terms that are relevant to relative sea level budgets in most places. Now, when I started out doing this, we focused very much on working in sort of a probabilistic framework. So our 2014 paper was all about probabilistic sea level rise projections, producing probability distributions. But over time, I've come to appreciate that may not be the most effective way to communicate unquantifiable uncertainties in sea level rise projections. So I want to just briefly introduce the distinction between quantifiable uncertainties and ambiguity. There's been a few versions of this distinction that have been used over the last 100-some years, going back to Frank Knight. I like Daniel Ellsberg's version. Daniel Ellsberg, gentleman featured there on the right, most famous for his role in leaking the Pentagon Papers from Rand, but he was at Rand because he was a game theorist and an applied mathematician who made quite a few substantial contributions to the field, one of which has to do with this issue of uncertainty versus ambiguity. So the thought experiment he used to illustrate this distinction was to imagine an urn with a mix of red and black balls on it. In one version of the experiment, that there's 50 red balls and 50 black balls. And most people would be willing to make a bet with 1-to-1 odds regarding which ball would come out if they're willing to make bets at all. The second experiment, that there's 100 balls and some are black and some are red, but don't know what proportions are each. And some really good Bayesians would still be willing to make a bet with 1-to-1 odds if they have an uninformative prior, but many people would be less eager to make a bet on that second one because people tend to be ambiguity averse. So the ambiguity reflects the fact that the probability distributions aren't quantified in the second case. Ambiguity is particularly a form of deep uncertainty, which is another term that's been used a lot in the last couple decades, in which analysts do not know or cannot agree upon key conceptual models or parameters. And I say use the term ambiguity as a form because deep uncertainty can also refer to a situation in which stakeholders disagree on how to value the desirability of different outcomes. Quite a different concept epistemologically, but a lot of the tools made for making decisions on the deep uncertainty work with both forms. Now, ambiguity has at some level been recognized in the earliest sea level rise projection literature. You go back to 1978, John Mercer writing on the potential, unknown likelihood potential for the West Antarctic ice sheet to contribute 5 meters to sea level rise in an unknown period of time. Over here on the left, over on the right, the picture I think is the paper that I have generally called the first sort of modern attempt to project quantifiable sea level rise projections, led by Vivian Gornitz at GISS, who include in their quantified projections the statement that it's not inconceivable that the situation is near a point in which continued warming and rise of sea level could cause rapid, highly nonlinear disintegration of the Antarctic ice sheet. We should emphasize that we have no evidence for such a process, and the sea level change we have deduced appears to be linear with temperature and largely a result of thermal expansion. Nonetheless, since sea level is at a high point in rising, the West Antarctic ice sheet warrants close attention. Right, so that is the essence of the ambiguity question, and it goes back to the very beginning of this literature. Nonetheless, groups like the IPCC have struggled with how to articulate that ambiguity. Various iterations of the assessment report have footnoted it, have said, well, these processes are highly unlikely if you go back to, say, a second or third assessment. Have just said, well, we don't know what to do with these ambiguous processes, so we're going to footnote it and then not include them at all. Or in the fifth and most recently sixth assessment reports have sort of struggled to include these in some way. So I'm going to talk about what the sixth assessment report did. But before I do that, I want to introduce the concept of what we call the sea level projection boundary change. So boundary chain. So this is actually generic. The figure is generically true about assessment, not just about sea level. But broadly, there's a research literature where lots of different groups may produce projections of sea level or of the driving contributions to sea level. Assessment processes like that of the IPCC or conceivably that of the National Climate Assessment, although that's not how the NCA has usually done this, draw upon this literature, assess the weight of the evidence, and synthesize them into a distilled set of sea level rise projections. The IPCC nominally is not supposed to do original research, but throughout its history, what the IPCC has done with sea level rise projections is sort of always been on the cusp of original research because it is trying to produce sea level rise projections that are consistent with the assessment of the literature on all of the individual driving processes. So, from that, IPCC projections then are often taken by regional assessments, such as the NCA, and then transformed into a form usable for adaptation policy and ultimately adaptation practice. Now, one of the distinctions here useful to think about is the distinction between sea level projections, which are scientific statements about the likelihood of different amounts of sea level over time under different emission scenarios and other assumptions like ice sheet sensitivity. And what I would distinguish as decision-oriented sea level scenarios intended to indicate trajectory of sea level change to guide practice. So in the US case, as I'll talk about in a second, right, the National Climate Assessment and the Interagency Working Group on Sea Level Scenarios, and the most recent iteration has started with the IPCC projections and then distilled them into a set of decision-relevant scenarios in red. If that doesn't happen at the regional assessment stage, and many states, in fact, do use projections rather than scenarios in their state assessment, at some point, in order for it to be used, somebody has to say, okay, use this set of numbers from the projections. And that would be the point at which, in some form, it turns from a projection into a scenario. So just talking a little bit about the steps here. So when the AR6 sort of came up with its sea level rise projections, the goal again was to distill down the research literature. And the approach we took was to develop something called the Framework for Assessing Changes to Sea Level, or FACS. The idea with FACS is that it allows us to take key terms in the sea level budget as they are represented in the literature and represent them in computational modules that link global climate to outcome, and then allow us to swap those modules in and out to think about different ways of how, say, different ways of modeling the ice sheets, what those imply about probabilistic sea level projections. So this is a framework we developed at Rutgers with NSF and NASA support. And it's built, the goal is going to get built, a framework built using modern software engineering best practices to facilitate the assessment of deep or structural uncertainty in sea level rise projections and their implications for global, regional, and extreme sea level. So one of the findings from this work is that, if we look at different ways of modeling the ice sheets, and in AR6 we looked at only 4 different ways, they yield different probability distributions. So these 2 figures here are showing you probability distributions from FACS and from the AR6 projections within FACS for global mean sea level rise in 2100 under a low emission scenario, SSP 1 2.6, and under a very high emission scenario, SSP 5 8.5, with 4 different approaches to modeling the ice sheets. So the 2 blue curves, the 2 thick blue curves, the ISMIP6 and LARMIT methods employ multi-model ice sheet ensembles, which we as the assessment panel judged captured processes in which there's at least medium agreement and evidence, and thus medium in confidence, which is why multiple model, ensembles of models can represent them. However, there are processes involving ice sheet instability that we know are not represented in those, but might still be decision relevant. So therefore, we also added 2 other PDFs. So one labeled Mickey here, where we incorporate a single ice sheet model for the Antarctic that represents marine ice cleft instability. And the other, SCJ, where we use a method called structured expert judgment, that's a study by Bamberg et al. 2019, to use people's brains to assess the literature, right? So the idea with structured expert judgment is that you take a bunch of experts who know the literature, you calibrate their ability to estimate uncertainty. So you're looking to identify those experts who not only know stuff, but also are good at estimating their uncertainty. And then you synthesize the results from those experts into probability distributions. So those 2 provide complementary approaches. But because they provide limited evidence, we regarded those as representing processes in which there's low confidence. So that's how we sort of used the framework for assessing changes to sea level to compute sea level rise projections globally and regionally with different ways of modeling the ice sheets. And then we had to synthesize those into outputs that could be intelligible and used. And so I will talk about that here. And I want to make the point that these choices are really important. Key figures and tables serve as boundary objects that get passed along what we call the boundary chain. So you might, like we writing as assessment authors might produce a table, and then that table is going to be the thing that people further working on policy or down here or working in regional assessment are going to focus on. Like we might have 100 words of text, or 100 pages of text, but what's in the table is going to likely be the thing around which discussions of application happen. So I'm going to go over this briefly because I'm sure many of you have seen this before, but this is the summary for policymaker time series for the AR6 projections. So highlighting 5 different emission scenarios and also highlighting one curve showing the potential impact from these low confidence processes. And this was really something we focused on ensuring was represented, all the way from the chapter through the summary for policymakers, was the idea we didn't want the low confidence processes to be buried simply in a footnote, but to be shown throughout. So bearing the time, I don't need to give you a lot of details. In 2100, projections are about 30 to 60 centimeters under low emission scenarios, 60 to 90 centimeters under high emission scenario, if you don't include these low confidence ice sheet processes. But another key message emerging from this is that the more you limit emissions, the lower the chance we could be surprised by these unknown likelihood instabilities in the polar ice sheets that could be caused by things like earlier than projected disintegration of marine ice shelves and widespread ice sheet instabilities, or faster than projected changes in Greenland. And that message quantitatively was brought through in the form that global mean sea level will rise above the likely range, potentially approaching 2 meters by 2100 and 5 meters by 2150 under very high emissions, cannot be ruled out. So those are sort of the global scale messages. In partnership with the NASA Sea Level Change team, which I was part of at the time and am now one of the co-leads of, we also timed with the release of the sixth assessment report, the NASA IPCC sea level projection tool, sealevel.nasa.gov/IPCC, which allows users to basically pull up figures for their location that correspond pretty closely to the figures in the main report for global mean sea level. And this has been extremely highly used. Ben Hamilton is the lead of the team, and I think he told me a few months ago, we've had relatively constant since it was released number of users in the hundreds of thousands of visits per month. So we end up with projections like this. So this is the Los Angeles projection, sort of corresponding to what we looked at previously for global mean sea level. And then I also want to point out this distillation from projections to scenarios, because in the US, in addition to having these probabilistic projections like the IPCC projections, these got distilled down in the interagency sea level scenario reports into a set of scenarios that are intended to span the range represented by the IPCC projections, and are provided with information about how to interpret their likelihood based on the IPCC projection. So I think this is from the NASA Sea Level Change Team tool for viewing the interagency scenarios, but I think it gives you a clear visual representation of what it means for these sort of probabilistic projections to be turned into scenarios to inform decision making. Finally, I want to conclude by talking about the value of information, because we put a lot of thought into how to communicate this, but what it means in the end depends upon the decision framework it's being used on. And so I will illustrate this with a paper. Actually, the reference is old. It's actually Fingerdahl 2025 in PNAS. It's been published. But the one thing, if you set up your decision so that you can adapt them over time and iteratively learn, you perform better economically than if you have your decision framework set up so that we need to know now what we are planning for the next 80 years. So in this study, Kai-Ru Feng, who's a postdoc, was a postdoc at Princeton, I've looked at an idealized problem for building a seawall around Manhattan under uncertain sea level rise projections. And what I'm going to show you is essentially if you take two different decision frameworks. So one is a one-shot decision, given the sea level rise projections we have today, and you're trying to optimize to minimize expected net costs, so the cost of the wall plus the cost of residual damages. You have two choices, right? You can plan for the high-end sea level rise, which is the SSP 5, 8.5, very high emission scenarios with these low confidence sea level projections, or you can plan for likely sea level rise. So SSP 245, the intermediate emissions, medium confidence projections. Well, so if you plan for the high-end sea level rise and you get the high-end sea level rise, you end up having a net cost of $3.2 billion. If you plan for the likely sea level rise and you get the high-end sea level rise, the cost is $14.8 billion. If you plan for the high end but get the likely sea level rise, the cost would be $2.3 billion. And if you plan for the likely and get the likely, the cost is $1.3 billion. So there's a concept in economics and decision theory called regret. So maximum regret is basically, how if you don't choose the optimum cell in this column, how badly off? Well, if you plan for high-end sea level rise, then your maximum regret is $1 billion from over-adaptation. If you plan for likely sea level rise, then your maximum regret is $11.6 billion from under-adaptation. Now, if instead of having to decide now how high you're going to build the seawall for the rest of the century, you constructed and set up the framework such that you build to some level and you have budgetary mechanisms and decision mechanisms so that you can actually increment it over time, the payoff matrix changes substantially. So in that case, if you plan for high-end sea level rise, but you do so in a way that where you're going to be incrementing the height of the wall over time, your maximum regret is only $100 million worth of, sorry, you compare this way. So $1 billion versus $0.9 billion, right? So if you plan for high-end sea level rise and got the likely sea level rise, the cost would be $1 billion. If you plan for the high end and plan for likely and got the high end, the cost would be $900 million. You would have saved $100 million if you had done that. If you plan for likely sea level rise and get the high-end sea level rise, then your cost is $3.9 billion. So if you had made the correct choice, you would have saved $2.4 billion. So your maximum regret goes from $11.6 billion to $2.4 billion. So it is, you minimize your regret by planning for the high-end sea level rise with a decision framework that allows you to adapt over time. So the value of restructuring the problem, if you know the right information, is somewhere between 400 and 1.7 million and 1.7 billion dollars. So that's a lot, but we have some time for discussion, and all of this is in these 3 papers, which you can see here.
Thanks, Bob. That was great. It's really interesting to see how you guys think through these problems with ambiguities, deep uncertainties, ambiguities. Okay, so let's open it up again. You can raise your hand or you can put it in the chat. It's kind of hard for me to see both at the same time. So, Kelly.
I wonder if you have any thoughts on, like, kind of given to your last point of there's a lot of value in not having to make an immediate decision of trying to price out differences between hard gray infrastructure versus green infrastructure that will itself adapt to whatever your climate or whatever your sea level ends up at over time, versus the trade-offs of course, it doesn't help you against like an 8-foot storm surge. Have you tried to cost out the differences between flavors of infrastructure in terms of their adaptability?
Ning's group at Princeton has that on their list of things to do.
Cool.
Yeah. I mean, okay. I think the challenge with some of the nature-based solutions is that they aren't going to be able to keep up at in the high end.
Yeah, Charleston saying, oh, by the way, I want my oyster reef to protect me against 12-foot storm surge. Like, the math doesn't math, but for like coastal marshes, when you're dealing with wave energy rather than height, it can help.
Yeah. Well, certainly in the near term, it definitely helps. I mean, like by the time you get to around 7 millimeters per year of sea level rise, a lot of the ecosystems have trouble keeping up. So in the tail, like they just get drowned.
That's a good point. See, other questions?
Question in the chat. I can read it. Let's see. It says the Hawkins and Sutton uncertainty framework focuses on sources such as model scenario and internal variability, but does not directly address issues of skill or credibility. Are there approaches or recommendations for linking uncertainty assessment to credibility evaluation?
So I mean, this issue actually comes up with the hot model problem in AR6. Right, and so the general Hawkins-Sutton framework, so that way of calculating variance just is looking at the models ensembles, but you would like to know, if some models perform better than others, right? And so in AR6 with the temperature and the global temperature and the global sea level projections, there was additional constraints from direct constraints on climate sensitivity. So one of the reasons we set up FACTS the way it was so that we could have climate projections that are driven by a model that represents assessed climate sensitivity and other assessed climate parameters, and not simply be dependent upon whoever is participating in CMIP6 and has deposited data and time. So that's sort of one set of problems, is where like the underlying ensemble models is broad and we can narrow the distribution within it. The other, which gets at the IC question, is where you have an ensemble that emits key processes that could be important or might not be. And yeah, I mean, where you get into that world, you're really no longer in a world in which your uncertainties are fully quantifiable, and so you have to rely on things like storyline or scenario analysis, and things like benefit cost analysis actually don't technically work because you no longer have probability distributions.
I think for some of these questions where it's really a one-off, like we're going to go through this transition exactly once, and we have irreducible uncertainty. I just think it's always worth remembering that these are social decisions, and like a lot of the answer has to be we should socialize them, like we should talk about them, we should suss out how people feel about things, and that pretending to a high level of numerical accuracy on these things is a little ridiculous. We just don't really know. Like there are some possibilities. They might pan out. We'll know more in the future. So like, I mean, the story you just told, Bob, is a really great story. Like it's a very illustrative story of like, make your procedures flexible, because when they're flexible, then you can learn as you go along. And that could potentially save you a lot of money. And that seems like a really good response to a problem of we don't really know what's going to happen, as opposed to, banging your heads against the wall and really trying to come up with a number for the odds where, the likelihood that we'll actually, I mean, we've been playing this game for a long time, right? I mean, the uncertainty around even the thing that's most well known, probably, how much will summertime morning temperatures in New York increase, if at the point of doubled, if CO2 doubling equivalent forcing. Like that's probably the thing we understand best, and our uncertainty in that question is maybe gone down a little bit over the last 30 years. So I don't know. I just think I really like the idea of gaming out the process and the procedures for how we're going to adapt to new information as we move along. And as a sideline, like this also emphasizes the importance of having a really good observational record, so that you have a really good null hypothesis that the trends will continue as they have up to date. Assuming in proportion to trends in forcing.
So I add to that. I mean, so that also points to the importance of sort of knowing what the decision and decision frameworks you're plugging into is. Like I presented a story because it's a scientific assessment story that starts with the literature and moves towards the end. But as you get to actually doing something useful, it's helpful to know what the decision is and then figure out what information is needed. Now, I mean, the other thing I want to throw out as a caveat, I mean, there's these sort of formal adaptive decision frameworks haven't made a lot of headway in the United States in coastal decision making, where they've made the most headway in places like the Netherlands and New Zealand, and I'm not sure why, but I can speculate that people know about them. But one thing is like, well, you actually have to have processes that can carry through on them, right? If you think that yes, what I showed is clear that the adaptive approach is best. But if what's actually going to happen is in 20 years, there's a 50% or 40% chance that the budget will materialize to make the next increment and a 60% chance it will just be pushed down the road, then you end up looking something that looks like a bad form of the decision matrix on the left, because you just did the thing that was sort of no regrets in the beginning and never are able to actually make the adaptive decision. So I think that there's that sort of policy uncertainty and sort of following through in a plan is a risk when we're talking about these adaptive frameworks. And if you're in a country with uncertain governance mechanisms, is a fairly real risk.
Oh, go ahead,
I just
Dan.
want to respond briefly to Kelly's question.
Yeah.
Utilities seem to have a similar setup to insurance, with a wide range of expertise and ambitions on climate, from having a big house team of experts to we need to keep the power on when it's hot, really. That's a great question. I again feel inclined to take it home and ask some folks who, I think that would be a great thing for the climate ready process to do as we move along, is write a little summary, of our interactions with utilities to date, and how, what our experience of people using these kinds of data has been. I don't have a great answer on the top of my head, except to confirm, yes, of course, there is a large range of knowledge on campus. Although I would say, by and large, my sense is that the utilities have pretty good, there aren't too many that I've interacted with that haven't thought about this stuff at all. But the regulatory environments in which they live are really, really different, and that probably explains a lot of the variance in their response to information that they, know full well, right? Because they can't typically they need PSC approval to make investments that might cost ratepayers something in the near future. So the regulatory environment matters a lot.
Okay, well, thanks to Dan and Bob. This has been really, I think, another great webinar, and we will be back on December 1st, and we will be sending out info. So thank you very much, and especially let's thank the speakers one more time. Bye.
Thanks, everybody.
Bye.